So the nice thing about calculating the change in entropy for any process involving an ideal gas is that we have a single equation. And so what that equation is it says that the entropy change of the ideal gas in going from state A to state B is given by the number of moles of the gas times the molar specific heat at constant volume times the natural log of the final temperature at B divided by the initial temperature at A. So you've got a ratio of temperatures plus, second term is mole of the gas times the universal gas constant R times the natural log of, and now we've got a ratio of volume. So the volume at state B divided by the volume at state A. For any process where we can draw out the process on the PV diagram, this equation works. It doesn't matter whether the process is isothermal or not isothermal. Though if it is isothermal, that means your two temperatures are the same, which means this ratio is 1. The natural log of 1 is 0. This term disappears. So if you have an isothermal process, you're just left with the second term in this equation. On the other hand, if you have an isochoric process that occurs at constant volume, the ratio of volumes is 1, the natural log of 1 is 0, and the second term disappears. So if you have an isovolumetric process, you just have the first term. But for any process, this equation works. Now, one of the things that we can do is come back and talk about a reversible adiabatic process with an ideal gas and recognize that for a reversible adiabatic process, so again, we've got to be able to draw this adiabatic process in our PV diagram, that the adiabatic says that we're not taking in energy as heat, which means that the entropy change has to be 0. So another way to think about a reversible adiabatic process, when we laid out the types of thermodynamic processes that we were going to deal with an ideal gas, the first three, isobaric, isochoric, and isovolumetric, something was being held constant. The adiabatic one was the one that was a little bit weird because it said its definition was simply that no energy was transferred into or out of the system as heat. But it looks like what we can do is say, well, isobaric is constant pressure, isochoric is constant volume, isothermal is constant temperature. But if we have a reversible adiabatic process, that is isentropic, meaning it's a process that occurs at constant entropy. So we can take advantage of this idea in terms of coming back and deriving something that we stated when we first started talking about engines, but we can see where the efficiency of a Carnot cycle comes from now. So we know that the efficiency of any engine is given by 1 minus, so the net energy dumped out as heat, its absolute value, divided by the net energy taken in as heat over your cycle. For a Carnot engine, we said that we can replace this Q out over Q in term by simply the cold temperature over the hot temperature, the ratio of the two temperatures at which a Carnot engine runs. So here's our Carnot cycle. So starting at state A, the system's going to undergo an isothermal expansion at the hot temperature. So this happens at a constant temperature. To state B, then an adiabatic expansion to state C, so it's dropping to a lower temperature. It's undergoing an isothermal compression to state D, where this occurs at the cold temperature for the system, and then an adiabatic compression back up to the hot temperature. So we've got two isothermal processes and two reversible adiabatic processes. So if we think about the entropy change over each process, well, in going from A to B, the system took in energy as heat, and that happened at a constant temperature. So I can calculate the entropy change during that process this way. For the adiabatic expansion, because that was a reversible adiabatic process, this is really isentropic. It happens at constant entropy, which means the change in entropy was 0 along our process from B to C. Our process from C to D was an isothermal compression, so again it happened at a constant temperature. So I can calculate the entropy change as simply Q over T, where now that Q was negative because it was dumping out energy as heat. And so I've just taken the minus sign out front and left the Q out in absolute values. From D back to A, again, that was a reversible adiabatic process, which means it's isentropic and the entropy doesn't change. So I can take these four calculations, and I know that they've got to tell me what the total entropy change is over the entire cycle. So just add them together. That's going to tell me the total entropy change over the entire cycle. Well, as we've stated, entropy is a state variable. So if you go through this reversible process, so the fact that we can plot it out on our PV diagram says that this is reversible. And so when you go through a reversible process and end up back at the same state, because entropy is a state variable, it only cares about which state you're in. We're back in the state we started, so the total entropy change over the cycle has to be zero. And so plugging in what we calculated for each of those four individual steps, what I've got is Qn over the hot temperature plus 0 for that first adiabatic process, minus Q out over the cold temperature plus 0 for the second adiabatic process. And it's easy enough to take this expression and solve, and what I see is that the ratio of the absolute value of Q out to Q in is equal to the cold temperature of the system over the hot temperature of the system. So this substitution of saying instead of thinking about a ratio of energy exchanges as heat, I can think of it as a ratio of temperatures, comes straight from thinking about the entropy change over an entire cycle using a Carnot engine.